So hello everybody. It's really a pleasure to be part of this workshop, and I'm very sad, of course, not to be able to be in person in Stuttgart and meet all of you, but this is what it is these days. So I realize I've given this overly ambitious and perhaps a slightly optimistic title. What do we know today about the 2D Hubbard model? And what I should really have said, paraphrasing Jean-Luc Godard, is more like something like 2 or 3 things we know about the Hubbard model, which is really what the talk is going to be about. Before I start, I would really like to warmly thank a number of collaborators with whom I've been working on this topic all over the years, and for many of them still involved in active collaborations, and especially Thomas, both for organizing this workshop, but also for a wonderful collaboration that took place over the last couple of years, and you're going to hear about in the first part of the talk today. So what is basically the purpose of this talk? So what I would like to ask is whether, with all the tools we have in hand, whether analytical or computational, we can now draw some overall consistent picture of the zoo of various phases that have been proposed and sometimes documented for the 2D Hubbard model. And what I would like to try to convince you about is that there are several key aspects of the physics of the 2D Hubbard model that can now be established beyond doubt, thanks to often the combination of controlled and accurate computation methods. And towards the end of the talk, I will also try to emphasize some important questions still open. Of course, we all know that the single band Hubbard model is a paradigm of strong correlation physics. It has become really an icon of the field, sort of Ising model of our field on which to test all our ideas and methods. It's not very often a realistic model for materials, but there is a happy class of materials for which it is actually reasonably realistic. And in my opinion, the copper-oxide high TC superconductors are such an example, but also a number of interesting materials, such that the 2D organic compounds, which have, however, geometrically frustrated lattices, maybe some iridates, definitely some twisted 2D materials like twisted TMDCs and other examples, and of course cold atoms in optical lattices. So this is just to establish contact with reality. I also want to say that there are some excellent recent reviews that are starting to appear on what we know today about the Hubbard model. These are 2 which are going to appear, I think, in Annual Review of Condensed Matter Physics. Thomas and some people attending this workshop are the co-authors of some of these reviews. And I've also given a set of lectures at the Collège de France this spring on the 2D Hubbard model that you can look at the website if you are interested. Okay, so my discussion will be admittedly somewhat cuprate-centric, but this is basically just to phrase the questions. You all know about this phase diagram here. I'm not going to comment in detail on the various phases, but we're going to, in the rest of this talk, mostly focus on the Holdo regime of this phase diagram, and especially ask questions about whether we can now claim that the pseudogap phenomenon in the strong coupling regime is understood. So I say cuprate-centric. This immediately raises a certain number of questions, like, does the Hubbard model display a pseudogap? If yes, what's the physical origin of the pseudogap? The pseudogap comes with the formation of so-called Fermi arcs. What are the Fermi arcs, and especially what happens to them as temperature is lower? Does the Fermi surface reconstruct, and how? And then, of course, there's the important question, which will be an important theme, a key theme of this talk, which is how does that match with other instabilities observed at low temperature, like stripes? And finally, I will probably not reach that point, but there is overarching burning question of whether there is actually superconducting long-range order at zero temperature in the Hubbard model. I'm not going to talk about that, but I also want to emphasize that there are other regimes which in which the questions are rather different, in which this model needs to be interrogated. And especially the field of cold atoms in optical lattices allows to address the physics of hot transport with fermions. And there are very interesting recent experiments that actually address this question. I'm not going to talk about this in this talk, but this is definitely a very interesting field. So the outline of the talk is basically the following. I'm going to start now with expressing some general and completely non-technical considerations on computational methods. What is the range of methods that are available to us currently? I'm going to forget many of them. It's going to be an incomplete list. I apologize in advance. Then I'm going to show how these methods can be applied to a weak coupling, or rather intermediate coupling half-filling case. That's the collaborative work with Thomas and many others that I mentioned at the beginning of the talk. We can consider this as a warm-up, although you will see that this warm-up is already a pretty tough exercise. And then I move on and talk about more intermediate and strong coupling, and in particular the theory of the pseudogap in the doped case. And finally, go into stripe territory and hopefully reach a handshake between these different questions. Okay, so let me start with giving you just the flavor, completely non-technical flavor, of some important classes of computational methods that are available to us today. And computational methods are not just brute force things you put on a computer. They actually come with some physically motivated idea, what I like to call an organizing principle for a given class of algorithms. And here I've put on these slides two classes of methods that have had their successes, which are organized around different organizing principles. So the first one is the one here in purple. It's the vast class of embedding methods, an ancestor being dynamical mean field theory and all its extensions, in particular cluster extensions. The organizing principle of these methods is spatial locality. So spatial locality means that any kind of incipient long-range order developing in the system still, we're going to look at this long-range order in a regime where the corresponding correlation length is small. Hence, we can expect the physics to be reasonably spatially local. And dynamical mean field theory and its cluster extensions takes full advantage, and other extensions takes full advantage of this locality principle. Hence, you can immediately guess that this is a set of methods which is going to be particularly useful when you come from high temperature, because that's the regime where the correlation lengths are small, or when you come from the high doping area. Then there is a different class of methods that have been immensely successful over the last, say, 30 years or so, which originally were purely zero temperature ground state methods, which are tensor networks and matrix-product states method. And we're going to hear more about that in subsequent talks, in particular by Uli later in this workshop. And the organizing principle here is entanglement. So the idea is that ground state wave functions and to some extent low-lying excited states have a relatively low degree of entanglement and hence can be efficiently represented using matrix product states with manageable bond dimensions. And the idea is really to leverage on this entanglement, on this low entanglement, and use a highly compressed representation of the wave functions. And in my opinion, an absolutely key challenge, which is a current frontier of the field and also in which I will try to convince you that a lot of recent progress has been made, is actually to realize some sort of handshake between these two classes of methods. Towards the end of the talk, I will show you some results using the so-called minimally entangled typical thermal state methods that, in my opinion, starts to realize this sort of handshake. Of course, the basic objects that these different methods handle are quite different. The embedding methods typically focus on the Green's function and self-energies. The DMRG and matrix product states method handle wave functions. And that's another difficulty in the field, which is to make these two talk to one another by looking at similar observables. There are, of course, many other methods, a vast class of other methods, these sampling methods. We have, of course, the good old determinantal Monte Carlo methods, like the Black-Decker Scalapino-Sugar method, which need to fight with the sign problem, for which methods like auxiliary field Monte Carlo have been invented. But more recently, and I'm going to describe this a little bit later in the talk, there's been wonderful progress using diagrammatic Monte Carlo methods, which really is a sampling by Monte Carlo methods of the perturbative series. And these has actually led to progress in the field. So I've given you some very broad brush description of the various classes of computational methods that some classes of computational methods that are currently being used. But what I want to insist on is that in the past 5 years or so, we've seen very valuable works that attempt at putting together more than one such methods and reach agreement on some piece of physics or some physics question using a combination of various methods. And we like to call these multi-method papers or multi-method collaborations because they often involve a number of people who have expertise in these different methods. And I've put on this slide a number of such recent papers. The Simons many electron collaboration has been in particular promoting this approach very much, and we're also pushing this very much at the CCQ in New York. This paper here at the bottom of the slide is what I'm going to talk to you about in the coming 10 minutes of the talk or so. And you will notice that several of these papers deal with the Hubbard model, but actually we are now seeing some attempts to do that, some successful attempts to do that on what you could call already materials. This is a beautiful multi-method paper on the hydrogen chain, which is a real, set of atoms that you actually simulate. Okay, so I promised we would start with a relatively easy case, and you'll see if that's actually easy or deceptively so, which is the weak coupling, or perhaps intermediate coupling, half filling, half fill, T prime equals 0, Hubbard model at U equal 2 in units of the hopping. So what else could be simpler in 2 dimensions? And you will see that computational methods are actually able to clarify completely the physics of this regime, but that one shouldn't overstate the easiness with which this can be done, and that this still requires substantial effort to really reach full understanding. So this is this paper here that I already mentioned. Thomas was absolutely the lead author of that paper, which involves a very large number of people from many different institutions. And the motivation of that paper was really to assess the current limitations of state-of-the-art controlled and accurate computational methods, but also to fully understand the physics in that regime, in particular the formation of the insulating pseudogap in that case, as we reach the old temperature, and test theories of the pseudogap based on spin fluctuations. So this is this paper, we've called this paper a multi-method, multi-messenger study of the 2-dimensional Hubbard model, paraphrasing our colleagues from astrophysics. The reason being that, well, this is definitely multi-method. I think we use 14 different methods in this paper, including 2 benchmark methods. And it's also multi-messenger because we look at the model using a large number of different correlation functions, each of one being a specific probe of a part of the physics. So let me start with sort of a mean field picture of the crossovers that happen in this problem. And for this purpose, DMFT is not about starting points. If you actually run DMFT for this for half filling in the 2-dimensional Hubbard model as an approximation, what you will see is that as a function of temperature and nu, all expressed in units of hopping, there are actually several important crossovers, but 2 of them are depicted, 2 particularly important ones are depicted here in red, this line, and in blue. So let me start with the blue line. Well, within DMFT, this is really a phase transition, not a crossover. Indeed, dynamical mean field theory being some sort of half of a mean field theory as far as spatial fluctuations are concerned violates Mermin-Wagner theorem, yields a second order phase transition into an antiferromagnetic phase. So this is this blue line. And you should really interpret that as determining a typical scale for the onset of strong antiferromagnetic correlations. We're going to see in which sense in the following slide. And then there is another line here, which is the red line, which is the typical scale at which you cross over from an incoherent high temperature soup to a regime in which you start having a degenerate gas of reasonably coherent quasi-particle-like object, so a metallic regime. So you already see that even at this very simple mean field level, there are like three important regimes: an incoherent regime, a metallic regime, and an antiferromagnetic regime with strong correlations. Of course, Mermin-Wagner replaces all these by crossovers, and reality is more something like this. So you recover these three regimes: incoherent, metallic, and pseudogap, quasi-insulating. But you will see that these two crossover lines, the red one and the blue one, have now opened up into two slightly different crossover lines. And the reason being that in reality, the nodal regions of the Fermi surface, which in this case is very special and fully nested, the nodal region and the antinodal region, because of the existence of a Van Hove singularity at the antinode, actually do not reach coherence exactly at the same temperature scale. The antinodal point reaches coherence at a lower scale than the nodal region. And similarly, the antinodal region gets gapped first as you cool down. So this is why these crossovers are now opened up into two crossover lines. And hence, there are really five different crossovers, five different regimes in this problem, plus of course the sixth one, which is the fully ordered T=0 ground state, antiferromagnetically ordered. So you see that simple as it is, this sort of intermediate coupling regime in the two-dimensional case is particularly interesting. And of course, each of these regimes has a specific signature when you look at a computationally accessible quantities like the self-energy as a function of Matsubara frequency. In the incoherent soup here, you have something that diverges at low frequency, and then it becomes coherent in the metallic regime 3. And then at very low T, the formation of the insulating pseudogap is again characterized by some sort of singularity at 0 frequency in that quantity. So looking at this quantity, one can actually diagnose these different regimes. So in this work, we've actually used two benchmark computation methods. By benchmark, I mean something which is controlled, accurate, and can be converged to basically the exact computational results. One is the good old Determinantal Monte Carlo, the BSS algorithm, and the other one is this recent progress on Diagrammatic Monte Carlo. I've listed on this slide some key recent progress, in particular going from traditional Diagrammatic Monte Carlo to what's called CDET, which is a determinantal formulation of it, due to Riccardo Rossi, that has really, which has really led to substantial progress in the field. And I have to mention that many of these, many very nice results were established for the 2D Hubbard model tweaked to intermediate coupling by Fedor Simkovich and co-workers using this CDET method. So in a nutshell, this Diagrammatic Monte Carlo method consists in generating the perturbation series. This slide here would be for the traditional DiagMC method, but now you have to think about it as generating determinants. And what limits the applicability of this method is that at some point some sign problem pops up, which limits the number of coefficients in the series that you can calculate, and importantly that you have to resum this series, and so you have to handle to make sure that the radius of convergence of the series can be properly managed so that you can reach convergence at the value of u you are interested in. These are basically the two questions: generating the coefficients and summing the series, that are the key challenges in this method. Nonetheless, this can be successfully implemented in this specific case, and this slide demonstrates that you see these different regimes. So each of these curves here is a different temperature for the imaginary part of the self-energies for nodes and antinodes. Each of the color correspond to one of these 5 crossover regions, and these 2 columns show you that the diagrammatic Monte Carlo and determinantal Monte Carlo methods actually basically very accurately agree. And so that one can claim that within this range of temperature, these methods allow for a complete computational solution of the problem, and in particular, determination that you see here of the various temperature scales that separate these different regimes. You see, however, that one cannot go to arbitrarily low temperature, and basically in inverse temperature, beta equals 16 is more or less what can be reached these days with these methods. Okay, so if we track a quantity which is a Monte Carlo proxy for the spectral function at zero frequency, you see very clearly here the opening of the pseudogap. So here is the soup regime, incoherent regime. Here is the regime where this spectral function grows, both at nodes and antinode as you cool down. So that's very typical of a metallic behavior. Correspondingly, the scattering rate goes down in a metallic-like way. And then when you reach this scale here, which is a little bit below 0.1, in that case, there is a dive down of the spectral function, which signals the opening of the insulating pseudogap. And you see, by the way, that if you simulate this problem with the magnetic phase DMFT, the order DMFT doesn't do such a bad job following this behavior. And correspondingly, when you reach the insulating pseudogap regime, the scattering rate at both the nodes and antinodes, but at slightly different temperature scale, explode and become very large. Okay, so an interesting point here is that, of course, we expect that at low temperature, from general considerations on thermally disordered antiferromagnets, we expect the correlation length to grow exponentially as we cool down. But you see that this growth of the correlation length actually takes place way before, already within the metallic phase, presumably, and actually approximately also exponentially, perhaps with a slightly different rate than in the regime where there is a charge gap. And in fact, it looks like the metallic regime is pretty resilient versus the fast increase of the correlation length. You see that you remain metallic up to correlation length of order 10 or so in units of the lattice space. So obviously, the growing of this antiferromagnetic correlation are responsible for opening the insulating pseudogap in that case. So this is a long wavelength phenomenon. And there is a beautiful theory of this that was put forward many years ago by Wilk and Tremblay, based in part on the so-called TPSC method, that basically amounts to analyze the opening of the pseudogap through these spin fluctuation kind of diagrams, semi-normalized couplings. And if I write some sort of Ornstein-Zernike plus Landau damping form for the spin susceptibility here, you see that there are two important scales in the problem. There is the correlation length, and there is another length scale which is set by the Landau damping, which is not very important in the low temperature regime, but which is important in the metallic regime. And this actually defines three regimes of temperature, just comparing these various scales together. There is a regime where psi, the correlation length, is smaller than the scale associated with the Landau damping. This is actually the metallic regime. There is a low temperature regime where psi becomes larger than the thermal de Broglie wavelength. And that is the criterion for the opening of the pseudogap. And what we checked in these computations is that indeed these various regimes that are described are very well delimited by this criterion, comparing psi to both the Landau damping scale or the de Broglie thermal wavelength. The way this happens, how this growing correlation length does open a pseudogap, was explained by Wilk and Tremblay a long time ago. If you actually evaluate the imaginary part of the self-energy with a growing correlation length at a hot spot of the Fermi surface, and here, because it's perfectly nested, the whole Fermi surface is hot, actually, you find that when the correlation length becomes larger than the Broglie thermal wavelength, the imaginary part of sigma becomes extremely large, of order t psi over Vf. So observe that this is larger than 1 when psi is larger than Vf over t. And that is the phenomenon which is responsible for the pseudogap. This is exactly what we see in our simulations. And indeed, this validates the Ville-Tremblay mechanism for the opening of the pseudogap at long wavelength antiferromagnetic fluctuations in this weak to intermediate coupling regime. So nice as it is, this analytical understanding can be compared to actual computational results. And what we see is that the simple spin fluctuation diagram actually works qualitatively. But as you see on this plot, which compares the actual results, which you can take to be this one, to such approximations in various incarnations, it doesn't really work quantitatively. And the reason can be understood by noting that the spin fluctuation calculation does a very poor job at capturing the overall local component of the self-energy, which, as you would guess from the speaker giving this talk, is actually very well given by DMFT, surprisingly. Actually, it turns out that in this, throughout the metallic regime, the single-side dynamical mean field theory approximation does an excellent job of capturing the local part of the self-energy, even though the correlation length can reach values of order 10 lattice spacings. There is an explanation of that for that I don't have time to enter into, but I refer you to the actual paper. So this obviously suggests to combine dynamical mean field theory, spin fluctuation theory, and this is my sort of poor man version of DGamma. This is DGamma without vertex corrections, like Thomas likes to say, which is just keeping DMFT as the computational method for the local components, and then using just a one loop spin fluctuation diagrams for the non-local components. And what you see here on this plot is that this does a very good job through all the metallic regime, and even qualitatively reasonable in the pseudogap insulating regime. Again, one of the surprising physical remark here is that happy quasiparticles can survive despite very large correlation length. And I think this has actually interesting applications for various materials, such as strontium ruthenate and iron superconductors. So this is basically what I wanted to tell you about weak to intermediate coupling. The take-home message being that in that case, available computational methods allow to completely nail down the problem down to temperatures, which are actually not that low, as you see here, but low enough to reach at least the beginning of the pseudogap insulating regime. And that this completely validates the basic mechanism for the opening of the pseudogap in the weak coupling regime due to the diverging correlation. So now I would like to take you into a different territory, which is the pseudogap at stronger coupling. So we're going to go now to a U, which is more like closer to 6. And to be a little more realistic in the context of cuprates, the results I'm going to show you are for a pretty large T prime over T, appropriate for whole dope cuprates, and a very low doping, 4%. And I would like to show you that in this regime, one can actually, in a controlled computational way, nail down the existence of strong coupling pseudogap by two different methods with quantitative agreement, one being the cluster extensions in the DCA flavor of dynamical mean field theory converged in the cluster size, which is a pretty formidable task, not possible for very many parameter range, but possible for that one, and diagrammatic Monte Carlo methods. And that work was very much the work of Wei Wu a few years ago when he was a postdoc at the Collège de France. He's now back in China. We like to call this parameter set the waypoint as being a reference point to which to compare future computational development. So just a very brief reminder about embedding methods. The embedding methods basically amount to divide, in the DCA form, for example, to divide the Brillouin zone into patches and to make a patch, to approximate the self-energy by a constant function in each patch. This maps the problem onto a finite cluster in a bath. And this is a set of approach, whether in the DCA framework or cellular DMFT framework or others, that has been pushed very much in the past 20 years by a number of groups in many places in the world. In the specific case at hand, this curve, which actually in this form was never published anywhere, surprisingly, but is related to the article I just showed you, demonstrate that diagrammatic Monte Carlo on one side and DCA extrapolated to infinite cluster size can be really made to match one another. The purple curve is diagrammatic Monte Carlo. The various data points here are DCA, and you see that this is following the self-energy along these paths. Path here in the Brillouin zone, you see that here around the antinode, im sigma is very large. That's what creates the pseudogap. And here you see that the various DCA results for different cluster size extrapolate to infinite cluster size exactly on the within our bars on the diagrammatic Monte Carlo value. So this is a clear demonstration that two methods allow basically to jointly solve the Hubbard model with agreement in that regime and demonstrate the existence of a pseudogap. And I want to emphasize that this pseudogap, here we are in a regime of the pseudogap formation, which is very different from the weak coupling pseudogap we had before. The correlation length is actually not large. And the formation of the pseudogap is largest at the antinode rather than at the hotspot. So in that strong coupling regime, the notion of hotspot, at least in that temperature regime, is not a relevant notion. Okay, correspondingly with the pseudogap formation, there is, of course, if you compute something like a contour map of the spectral function, there is, of course, the formation of apparent Fermi arcs with more intense quasiparticles near the nodes and less intense in the pseudogap near the antinodes. So what is the physical origin of the pseudogap? Well, here we can resort to a beautiful set of tools that were pioneered by our chairman, and by Ole Gunnarsson and co-workers, which is the so-called fluctuation diagnostics, which I don't really have time to describe in detail, but which is basically a way to do a surgery of the self-energy and understand what are the fluctuations that dominate the self-energy. And of course, this was first done with DCA with a certain momentum resolution. The diagrammatic Monte Carlo allows to do that with very, very good K resolution. In this work with Wei Wu, we actually applied this method and demonstrated that the pseudogap is actually due to pi Q equal pi correlations associated with antinodal physics. So it's really the physics of commensurate antiferromagnetic correlations with not a very large correlation length, which is responsible for the pseudogap opening. So the take-home message of this part is that actually progress in computational methods, both diagrammatic Monte Carlo and cluster extensions of DMFT, allow to establish that the 2D Hubbard model does develop a pseudogap at small hole doping in the intermediate to large U over T regime, and that its physical origin is short-range antiferromagnetic correlations, not other types of correlations.
Antoine,
yes.
You have about 5 minutes talking.
Yes, I know. Thank you, Thomas. I'm going to have to cut it short a little bit, but hopefully not too much. Okay, so one can actually, thanks to the calculation of also two particle response functions, make pretty good comparisons to experiments on cuprates. These are some work by Manuel Gull and co-workers for the night shift and for the NMR relaxation rates that are very similar to what is observed experimentally in the whole dope regime of cuprates. But basically what I would like to tell you in the few minutes that remain is how do we actually reconcile that with the very large body of evidence that documents the existence of stripes and incommensurate spin density waves at low temperature or zero temperature in the weakly doped Hubbard model. So that goes back to the early days of ITC. Even static mean filter of the Hartree type has, and that's how they were theoretically discovered, has stripe formation. These are two very beautiful papers that demonstrate that. And of course, since then, a number of methods have shown that at low doping in strong coupling regime, there is the iconic picture of a stripe which is being formed, namely a linearly polarized spin density wave, which you see here in red, and holes living preferably near the nodes of the spin density wave, hence with a spin wavelength which is twice that of the whole of the density wavelength. So this has been confirmed by a very large variety of methods, DMRG, IPEX, auxiliary field Monte Carlo, DMET, and so on. And by the way, this is a very well-known paper about this. And by the way, this is also seen by dynamical mean field theory. It's actually a common misconception that DMFT and cluster extensions do not find stripes. Actually, this is not correct. The confusion comes from the range of temperature being addressed, and most importantly, by the fact that often DMFT is looked at in an unrestricted, in the sense of unrestricted mean field way. If you allow each side to do whatever it wants, and there is a beautiful paper by Peters and Kawakami that I show here that demonstrates that, you do find, even within single-side DMFT, beautiful stripes forming at 0 temperature in the Hubbard model. So how do we reconcile all that? This is also some work by Thomas that actually shows that as you cool down, the commensurate correlations I was talking about earlier actually do deform into incommensurate order. Sometimes this incommensurate order persisting up to pretty high T, actually, such as in this work. So how do we reconcile all that? So the emerging picture, qualitative picture at least, that emerges of all this is that if we are at relatively high temperature, let's say hopping over 5 or hopping over 10, we have a regime which is dominated by commensurate spin correlations and a pseudogap due to these commensurate spin correlations. And then as we cool down, these spin correlations may generically become incommensurate. And at low temperature, the ground state is striped ordered with both an incommensurate spin density wave and a charge density wave. And I want to conclude this talk by showing you that actually this can be documented by recent progress. And that's basically the handshake notion I was promoting before, by recent progress that put together methods that uses tensor network methods and sampling ideas. So this is the so-called minimally entangled thermal typical states method. This is a collaboration led by Alex Vitek, who was the main leader of this collaboration and did most of the work for this work, in which we actually, using the METs, find this different regime. And this is basically illustrated on this slide, in which what you see here is the charge and spin structure factor as one goes down in temperature. And what you see here is that the spin structure factor at low temperature is peaked. So this is actually inverted. This is spin and this is charge. The spin structure factor is incommensurate at low temperature, but then at higher temperature becomes commensurate. While when the correlations become incommensurate, at the same time, charge modulations develop in the system, so stripes appear. So this sort of validates this qualitative picture I was showing you before here. Okay, and the METS method is actually a combination of tensor network representations of the wave function plus sampling among these wave functions by basically sampling quantum values, Monte Carlo values. Okay, so this is my conclusion, take-home message. I hope to have convinced you for this talk that the consistent overall qualitative picture and sometimes quantitative agreement between different methods emerges for the two-dimensional Hubbard model at low hole doping in the strong coupling regime, that in this regime, the Hubbard model displays a pseudogap whose origin is now, I think, well established to be associated with short-range antiferromagnetic correlations, but that at lower temperature, incommensurate spin correlations and stripe formation do develop, and that very interesting and exciting set of developments realize some sort of handshake between computational methods, allowing to establish this overall qualitative picture. There are, of course, many open questions, but instead of reading them out loud, I just leave them on that slide. Thank you.